Today we are going to study the topic of curved beams. Usually, or in most cases, we would see these kind of straight beams which are being simply spotted or either cantilever beams in most of the cases. But sometimes you might have seen in the houses or in office buildings or in multi-story buildings, there are some cases where it is not possible to provide these straight beams due to the space requirement or sometimes due to the architecture requirement. For example, the architecture may specify that over here we need to provide the curved beam. So in that case, the structural engineer can't do anything. He is supposed to provide that just for the sake of the view of the building or whatever you can call it. So obviously for this straight beam, we have the formulations for the calculation of stresses, and based on those stresses, we can design these beams, or we can, by design of beam, we usually mean that we how what number of bars should be placed in the beam, what should be the dimensions of the beam or dimensions of the cross section. So first and most important thing is obviously the calculation of stresses in these kind of beams. But obviously, these formulations are valid for the straight beam. Here you can see some example of the curved beam. This is one sort of curved beam with a center of or radius of curvature over here, or this may be the distance r from the curvature, or this distance can be represented at capital R. But in the case of curved beam, also the important thing is that these cross sections are same as in the case of the normal straight beam. For example, for this beam, if you see that this cross section over here is the I section, right? Similarly, for this beam, the cross section is a rectangular cross section. So the type of cross section or type of the sections that we use for the construction of this curved beam are similar to what we have in the case of simple straight beam or the beams which are normally used in the construction. But for these beams, the formulation of stresses are quite different from what we have. We can't apply these ones because in this we have to take into account the factor of radius and the distribution of stress. For example, in the straight beam, if you have a rectangular cross section, the distribution of flexural stresses in this beam are something like this one. But this is not the case in the case of curved beam. In the case of curved beam, this distribution is hyper non-linear, or they can call it a hyperbolic function or something like this one. So to figure out the stresses, we obviously need some formulation. So today's topic, or the focus of this whole topic, is to derive some formulations for the calculation of stresses in the curved beam. And in the case of straight beam, usually if we have a rectangular cross section, the neutral axis coincides with the centroidal axis of the beam. But in the case of curved beams or a curved cross section, the neutral axis may be above or below this. I will tell you the reason why it is above and below later when we are done with the derivation. Then you will understand why it is above and below the cross section of the section. So anyway, this neutral axis is not right on the the centroidal axis. So we need to the second thing that we need to figure out is how to determine the location of neutral axis in case of curved beams. And the third thing is if we can correlate, for example, over here, if we know the movement y distances and I, we can calculate the stresses. So this relationship is basically the correlation of stress and movement. And the third thing or final thing that we need to do is to correlate these stresses with the movements, or have some relationship for stresses and movement, so that we can calculate the stress at any cross section if we know the movement and its distances or y distances, or in this case, or in the case of curved beam, the r distances are of importance. So the derivation is quite simple, and Some of the steps which are involved we have already done in the elastic beam 3D derivation. So it is quite simple and related to that and rest of the steps you have done in the calculation of flexure formula. So the same approach will be applied over here and we will have a relationship for stress and moment that can be used to calculate the stresses in the case of curve. So let's suppose that this is one cross section which we have taken from a curved beam, and this is the radius of point of curvature. And if we are measuring the distances, then this r dash distance over here is the distance or the location of centroidal axis. This is not available on the slide, so I'd suggest to make your own notes because I have taken some parts from different books, so even in the books, the whole derivation won't be same as we'll be doing in the class. So this R dash is the location of centroidal axis. This small r is the location of any random distance or any random area dA for which we will be deriving this equation, and then obviously we know if we take the integral we can apply it over the whole cross section. So this r is the distance of dA, which is any random area, any random differential area from center of curvature. And this capital R over here is the distance from the center of curvature to the neutral axis or the neutral surface. You can see over here that this centroidal axis is not exactly on the neutral axis. It is a bit low and neutral axis is a bit high. So this capital R is the distance of neutral axis from center of curvature, right? So now the first thing is we need to figure out the stresses. If we can calculate the stresses in this small element or in this fiber AB, and then we can apply it to the whole cross section um, of this curved beam. So for that, the first thing is if we know the strain, we can calculate the stresses based on this relationship, that is stress is equal to epsilon into modulus of elasticity. So for that, we need to know the strain. So by strain, that is a simple calculation that if you know the change in length over original length, you can figure out the strain. So if we take this fiber AB over here, which is shown over here, and we suppose that this is its length before any type of load is being applied or before any deformation is being produced. And this is this length A dash V dash after the section or after the loads have been applied and due to the applied load, the internal movement is being produced, and these internal movements will cause or will produce the deformation due to which this length AB will change. It can increase or it can decrease. So the purpose is that this length A dash B dash has changed. So now from this figure, can anyone tell me that what should be this length AB or what is this length AB?
L is equal to r theta कर लेंगे सर.
R into d theta, yes. So this length AB, before the original length is R d theta. So I can write over here that the original length AB is equal to R d theta, and what should be the change in length? For example, after the load has been applied, this R or the distance of that from the neutral axis or distance of the neutral axis from center of curvature, obviously it would change slightly. So it may change to R dash, and this angle theta would also change, so we can represent it by d theta dash. And over here, this R factor or this distance would also change. But just for the sake of simplicity, so we don't have too much complexion, we are not going to consider this R dash at this stage. We will assume that this difference, which is the difference between the neutral axis distance to this AB distance, will remain almost similar because maybe this R factor will change and this R dash will also change. but this difference between them will remain similar to what we have to the distance before deformation and after deformation. This difference would remain the same. It won't, although it is possible that it can change a bit, but for the sake of derivation, we would assume that these distances would remain same. So in this figure, if I want to show what should be this length A dash B dash, can I say that this length is equal to R dash plus this length R minus capital R into d theta. So this is the length after this section has been deformed. So this is the original length and this is the final length, that is R dash plus R minus R into d theta. So if I simplify it a bit, I will get A dash
कैपिटल कैपिटल आर डैश क्या सिग्निफाई कर रहे हो?
after the deformation, this length R, which is the distance of this neutral axis from center of curvature, it would obviously change a bit. Either it will increase or it would decrease. So we will represent it by R dash factor after deformation. So it is the same distance of neutral axis, but it won't be same as this R, right?
Right, sir.
So if I simplify this a bit, I will get R dash d theta plus R d theta minus R d theta. Now you know one fact for sure, or the simple definition of neutral axis is that the neutral axis is the one which does not undergo, and on which neutral axis is the one on which the stresses are zero. Is there any question?
सर ये डी थीटा डैश नहीं होगा इसमें?
Yes. So for neutral axis, or at neutral axis, we know that the stresses are zero. So that means that the length of neutral axis before and after deformation, if this is the length before deformation, then the length of neutral axis after deformation is same, because on this axis the stresses, or there won't be any type of stresses that would occur on this neutral axis. So if I see from this figure, what is the length of neutral surface before deformation? That is R into d theta, right? So this length is R d theta. And what is the length of neutral axis after the deformation occurs? R dash d theta. So since there are no stresses on neutral axis, so we can say that R d theta is equal to R dash d theta dash. So if I replace this factor into this equation, I will get R dash d theta dash is equal to R d theta plus this will remain same as R d theta dash minus R d theta dash. So this is the final length and this is the original length, that is small r d theta. Now if I substitute into the strain formula, the strain formula is change in length. Change in length is obviously the final length minus the original length. So the final length is this one. If I replace it into this equation, I will get r d theta plus r d theta dash minus r d theta dash. This is the final length minus original length. So the original length is this one, that is small r d theta. So I would replace it over here minus, I would write it here. This is L, that is r d theta. This is the original length divided by original length, that is again r d theta, right? So if I simplify this one, I would get epsilon is, I have two terms for small r and two terms for capital R. So if I take small r as common, I will get r d theta dash minus d theta, and this minus capital R as common, so I will get d theta dash minus d theta divided by r into d theta. So this epsilon is represented as, if I again take this factor d theta dash minus d theta as common, I will get r minus capital R divided by r into d theta. So again, if I simplify it a bit, I will get epsilon is equal to d theta minus d theta over d theta r. From here, if I take this r factor as common, I will get 1 minus capital R over R over here. So the strain will be d theta dash minus d theta over d theta into 1 minus capital R over R. Now this vector over here, this vector, this vector is a constant. For example, before and after, for example, when the load will be applied, if we see into this figure, initially this vector is d theta, is the angle between these two radius of curvature. And after the load is being applied, this vector will change from d theta to d theta dash. So once we know this vector for one type of a beam or one type of a strip, it will remain constant. And once we can calculate this vector, we can simply, this value will remain same for different points in the cross section. For example, if I want to calculate the stress is at this particular point, this vector d theta minus d theta over d theta dash will always remain constant if we have this point, or any point over here. So we can represent this vector as a whole, or replace this one by a random constant value, that is phi. So the strain will be phi into 1 minus r over capital R. And if you see closely into this factor represents one type of a strain, that is the strain in this angle d theta. This is the final angle d theta dash. This is the original angle, and the change in angle over original angle. So this factor phi can be represented as the strain in this angle theta, right? So this is also one type of a strain. Anyway, it remains constant for one type of a beam or for one type of section. And now this is the relationship for the strain in the section. And since we are interested in figuring out the stresses, so we know that the stresses for the elastic material, the stress is strain into modulus of elasticity. So if I replace this strain into this equation, I will get the stress as E into phi into 1 minus capital R over R, right? So this equation represents the variation of stresses as the distance r, which is the distance of this random distance or random fiber from the center of curvature. So this r over here is a variable factor. This capital R represents the location of neutral axis. So previously, in the case of simple beams or the straight beam, we had this relationship where the stress is my over I. So for a random cross section, if we plot the stress distribution, it won't be linear. Just like I have shown you for the straight cross section, the stress distribution was something like this one, right? But in this case, the stress distribution will follow this curved path, this path. It won't be a linear just like this straight beam which is shown over here. It will follow the curved path. So when the stress distribution is curved, we know one thing is for sure, that let's say this is the centroidal axis, then it is in like 95, maybe there will be one or two cases where the stress at the top is equal to the stress at bottom, or the stress and the tension is equal to the stress at the compression. So it is not always the case that exactly above the neutral axis there will be the stresses sigma t, and below the neutral axis there is this stress sigma c. So it is not always the case that sigma t is sigma c directly above and below the centroidal axis. So for the case of neutral axis, we know that the ये जो stresses हैं for neutral axis, the stresses should be equal above and below the neutral axis. So since this distribution is not linear, so that is why the neutral axis will not coincide with the centroidal axis. It will be either maybe above the centroidal axis, or it may be below the neutral axis. So it completely depends on the distribution of neutral axis. So in the case of curved beam, just remember one thing, that this neutral axis is not directly on the centroidal axis, because the stress distribution is non-linear. So it is possible that this stress above the centroidal axis can be greater than the stress below the centroidal axis. So just to balance these two stresses, or to satisfy this condition, our neutral axis may have to move upward, because for neutral axis sigma t minus sigma c should be 0. So this is what I was telling you before. So this is the equation for, yes.
सर हमने मतलब अज्यूम किया ना कि जब लोड लग रहा है तो आर कैपिटल आर में फर्क आ रहा है, वो आर डैश हो रहा है, तो
Yes.
आर माइनस आर में क्यों नहीं चेंज आ रहा? एज एन उसमें भी तो डिफॉर्मेशन हो सकती है.
Yes, this is what I was telling you. कि ठीक है, आर डैश जो है ना, मतलब हमने इसमें आर डैश फैक्टर नहीं शो किया, तो आर डैश में भी चेंज आना चाहिए था आफ्टर डिफॉर्मेशन. लेकिन हमने क्या किया, although maybe it is possible that आर, अगर ओरिजिनली आर 20 था और स्मॉल आर लेट्स से 10 था, तो जब डिफॉर्मेशन हो गई तो आर डैश जो है लेट्स से 25 हो गया, और स्मॉल आर जो है वो 15 हो गया. तो इनका डिफरेंस क्या आ रहा है? अगर इस केस में r माइनस आर जो है वो 10 था, तो इस केस में r डैश माइनस आर डैश क्या आ रहा? 10, राइट. तो इट इज
राइट सर.
पॉसिबल कि ये थोड़ा बहुत चेंज हो जाए, लेकिन डिफरेंस जो है इतना वेरी नहीं करेगा दोनों केसेस के लिए, बिफोर एंड आफ्टर डिफॉर्मेशन. सो इसीलिए हमने ये एक अलग या तीसरा वेरिएबल इंक्लूड नहीं किया, जस्ट टू कीप कि हमारी इक्वेशन जो है वो थोड़ी सिंपल है. ठीक है.
ठीक है सर.
So this is about the strain. अब सेकंड थिंग कि हमें न्यूट्रल एक्सिस की लोकेशन भी फिगर आउट करनी है, बिकॉज इससे हमें ये चीज़ तो श्योर होगी कि स्ट्रेस डिस्ट्रीब्यूशन लीनियर नहीं है और न्यूट्रल एक्सिस सेंट्रोइडल एक्सिस से कॉन्साइड नहीं कर रहा. तो फॉर द लोकेशन ऑफ न्यूट्रल एक्सिस, so neutral axis we know that the stresses are zero. So this is the equation for the stress that we already have. But this stress equation is for one particular area or differential area dA. So if I integrate this equation with respect to total area, I will get the total stress. So for the neutral axis, we know that the stresses are zero. So I will apply this condition that the total stress which is acting on the cross section is equal to 0 at one particular fiber, and that fiber is our neutral axis. So based on this condition, we will make one derivation for the location of neutral axis. So we know that this stress which we have just calculated this equation is equal to E phi into 1 minus capital R over R. So if I replace it over here, I will get E phi into 1 minus capital R over R, EA is equal to 0. So this E phi factor is constant, so I can take it out. This area 1 minus capital R over R into dA, right? So if I further simplify this one, I will get E phi into area 1 into dA minus E phi, or I can do that. This E phi is constant. It can go on to that side and this term will be 0. Okay, so we will be left with this term area into dA and the second integral is capital R over R dA is equal to 0. So this R can come out because it will remain constant or it is one particular distance. So this R A 1 over R dA is equal to 0. So this term can go on to the right side. So we'll have, what is this factor? Or what is this integral? Can I say that this integral is A? Is there any confusion about this one? If you simply integrate it, you will get, let's say, like a random variable x, and if you substitute this limit A, you will get the answer as area. So this integral we have solved is equal to A, and if I take this factor over here, I will get 1 over R dA is equal to 0. So if I take this whole term, if I take this whole term on the left side, I will get the equation of R as A over integral A 1 over R dA, right? Now, this is the equation which is being used for the calculation of the location of neutral axis. Now, this term over here at the bottom represents the integral of 1 over R, which is a factor. This 1 over R term. So, this is the R term. So, that bottom term represents the integral of 1 over R with respect to the total area. So to figure out this factor, for example, if we have a rectangular shape, let's just do it for one shape to understand that how it works. Now this is the general equation. Now if I want to apply this to a rectangle, for example, if I have a rectangular cross section and I want to uh, figure out that what this integral should be. So this R distance or the range of this R distance are obviously, if this is the center of curvature, then this R or the range of this R is, let's say this is R1 and this is R2, right? This is the width of this rectangular cross section, or you can say circular cross section. If I take the differential area on this side or of this element, what would be this length? I can represent it by dr. This is any random length. So the differential area will be dr into b. So this factor will be 1 over r dA, that is equal to r1 to r2 1 over r. What is dA from this figure? If this is the differential area, that will be b into dr. So what is the integral of 1 over r? Anyone?
ln
Eh? Log natural r, and r1 to r2. So if I simplify this one further, I will get log natural r2 minus r1. Okay, so I can represent this integral log natural r2 over r1. So if you have a rectangular cross section, that then this integral, which is the denominator in that term of capital R, is represented by this factor. But obviously for the rectangular cross section, it is simple to figure out the values or to solve this integral. But in the case when the cross section may be is a rectangular, is the triangular or a circular cross section, then it can get complex to figure out this integral. So for that case, we have been provided the values of this whole factor for different type of cross section. For example, for the rectangular cross section or a sphere cross section, we have just derived the values of this integral, right, which is this one. But in the case when there is a trapezoidal cross section, then it becomes difficult to solve this integral. So for these cases, we have the predefined values of this integral and we can use directly in our formula. These distances are the distance from the center of curvature to the top and bottom this R2 and R1, this B1 and B2, you can see are the dimension or the width of this trapezoidal section, and there is no other factor. Similarly, for the circular cross section, if we know the distance from the center of curvature to the center of circle, and if we know this range is this area or the radius of this circle, we can figure out this factor directly by using this equation. So to make it easy, there are some tables available for different type of cross section to figure out this whole factor. And after calculating this value, we can substitute into this equation and simply we can get that where is our neutral axis situated. So this is about the location of neutral axis, and the final thing that we need to do is to correlate the stresses with the moment. So to correlate the stresses and movement, we know that we will simply use, if you can recall that you have used one condition in the flexure formula as well. So for example, let's assume that this cross section over here is similar to this one, because this is also a random cross section and this is also a random cross section. So this is the differential area A on which we have calculated the stress equation, right? So if I want to know what is the force or what is the resultant force, so that resultant force may be coming out of the paper. So I can't show it exactly correct over here. So let's assume that this is the resultant force which is coming out of this board or out of this paper. So this force, if stress, we have calculated one equation for stress. So if I want to know what is the force, the force is stress into area. So this, for this differential element, the area is dA. So the force will be stress into dA. So this is the force. And another thing which is acting, or the other forces that are acting, are this moment M, which is also the same moment which is shown in this figure, right? So this moment M. So if I want to calculate that how much resultant force is acting on this neutral axis, so that will be, or the equation for this resultant force on this neutral axis will be sigma into dA multiplied by lever arm, which is represented by this y distance, and the other force that is acting is obviously this movement. So I am basically taking the moment about neutral axis. So the moment that is acting about neutral axis is this M, right? So this is the net force which is acting upon the neutral axis. So by using this simple relationship, I can correlate the moment with the stresses, and I can simplify it to include these factors R, capital R, and small r. So over here you can see one thing, that this y distance is the difference between this distance of neutral axis, that is capital R, and the distance of this differential area. So y is equal to capital R minus R. Now we have an equation and we will just simplify it to correlate moment and stresses. So the equation that I've written over this, and another thing is that that moment was dn, because we are taking the differential element on which the moment is acting. So obviously that moment will also be differential moment. So y is equal to y into sigma dA. So the differential moment is equal to y is equal to, obviously, so if I want this y is capital R minus R into sigma dA. Now, if I want to apply it over the whole cross section, I will take the integral to remove this differential factor. So if I take the integral, I will get moment is equal to integral capital R minus R. This sigma factor, the equation we have already derived, that is the same equation, E sigma into 1 minus capital R over R, right? If I substitute into this one, I will get E phi into 1 minus capital R over R into dA. So if I further simplify this equation, I will get the moment as this capital R minus R. This E5 factor will come out over here. Actually, we have made, I think, a small error. So we can see it later. So if I take the LCM, so this will become R minus capital R divided by this small r and this differential area A. So yes, we have made one mistake. In this figure, if you see that both these movements or this force is producing the counterclockwise movement about the neutral axis, and this force or this movement capital M is also being produced in the counterclockwise direction. So if I have to take the movement about the neutral axis, it should be plus M is equal to 0, and then this M will go on to other side and we will have the negative sign with this movement, that is negative M. So this is one.
फिर opposite नहीं है sigma dA और m के directions?
This sigma dA is coming out. So if I am taking the moment about neutral axis, so it will rotate something like this one, right? It is coming out of the paper. And I want to take the moment about this neutral axis. So it is also producing the moment in counterclockwise direction.
सर m एक्सटर्नल होगा मूवमेंट ये आपने अप्लाई किया
Due to the external forces, the internal movement जो produce हो रहा है. Okay.
ये m जोन्स आपने एक्सटर्नल लगाया, ये एक्सटर्नल मूवमेंट आपने दिया इसको
जो एक्सटर्नल फोर्सेस लगेंगी आपकी मेंबर से, उससे जो मूवमेंट प्रोड्यूस होगा, यस एक्सटर्नल मूवमेंट
या इनके डायरेक्शंस मतलब ऑपोजिट ही होंगे हमेशा मोमेंट, और मतलब m तो आपने अज्यूम किया है ना कि
मतलब फॉर द सेक ऑफ दिस डेरिवेशन हमने ये अज्यूम कर लिया, लेकिन जब हम क्वेश्चन में जाएंगे तो ये हमारा क्राइटेरिया बन गया, तो उसमें आप देखेंगे फिर कैसे हम इसका साइन चेंज करेंगे, बट यूजुअली जरूरत नहीं पड़ेगी आपको चेंज करने की, वो सेम ही रहेगा जो भी आपकी फाइनल इक्वेशन है, यू जस्ट हैव टू यूज इट डायरेक्टली, राइट?
राइट सर.
So over here, so we will have this negative sign over here and negative sign over here, this negative, and if I take this negative onto this side, I will have a negative over here, and if I multiply this negative sign with this term which is inside, so I can show it over here, that will turn out to be E phi integral capital R minus R, and this term will be R minus R divided by R into dA. Now we have the same, these two terms are same, so we will get M is equal to E phi, and if I solve the square root of this one, I will get capital R square plus R square minus 2 capital R small r divided by R into dA. So this movement will be E phi integral of R square over R dA plus R square over R dA minus 2 into R over dA. So this R will cancel out with this one, this R will cancel out with this one. So we will be left with E phi. This R square is constant, so we will have 1 over R dA plus integral R dA minus 2 into capital R integral dA. So this integral over here is what? Area, right? And for this integral, we already have one equation, which is this equation over here. So can I say that this integral factor is 1 over r dA is equal to capital A over r. So we have the equation for this integral, which I will substitute in this equation that we have derived just over here. So that integral is equal to capital A over r. So I will replace that factor over here. So m is equal to E phi into r square multiplied by capital A over r plus, and this integral will be minus 2 r into area. So can anyone tell that what is this integral? Can you think of something?
सर 1/2 तो
इनर्शिया
नहीं
वाला
है
तो नहीं कुछ
So if you remember, अगर हमने किसी
मोमेंट
शेप का सेंट्रॉइड फाइंड करना हो तो दैट इज आर डी ए ओवर ए, मतलब किसी भी रैंडम डिफरेंशियल एरिया का मोमेंट आर्म उसका इंटीग्रल डिवाइडेड बाय टोटल एरिया, राइट? यही होता है किसी भी शेप का सेंट्रॉइड। तो अगर आप इस ए फैक्टर को इधर ले जाएं तो दैट विल बी आर डी ए। तो this integral we have over here, so it is the same integral. So if I replace this factor r dash by r bar a, so this will give us this equation. And if you remember, initially we have defined this r dash distance, that is the location of centroid of this cross section. So if I simplify this further, that will cancel out. So m is equal to E phi ar plus r bar a minus 2 ar. So it will be m is equal to E phi r bar a minus capital AR. Yeah. So if I take this a as common, I will get r bar minus r. So this is one equation for for the moment. Now if I calculate this E phi, so that will be m over a into r bar minus r. So let's call this equation as 2. And if you see, we have the relationship for stress, which is this relationship, right? So if I replace this factor E phi in this relationship with the factor E phi that I have just calculated, then I can correlate these two moment factors. So I can call this as 1 and just write over here, substitute equation 2 in equation 1. So this will give me sigma is equal to m over a r bar minus capital R into 1 minus r over r. So this is the governing equation for the curved beam. So if you know the internal moment, if you know the area, if you know the location of centroidal axis, the location of neutral axis, and you want to calculate, this is the random distance r if you remember, and if you want to calculate this stresses at any point in the cross section of curved beam, then you will substitute this r distance for that point. All other factors are constant and will remain same for one type of a beam. Only this small r will be one variable. So if you replace that factor r for different points, then you can get the stresses at different points in the beam. So this is it about this lecture. We have derived the relationship. In the next class, which is scheduled for 11 p.m., 11 a.m., we will solve one numerical problem to see that how this equation works. So for now, if you have any questions about this one, you can ask me.
लास्ट में जो आपने सब्स्टिट्यूशन की है ई थीटा की वो जरा एक बार फिर से बता दें.
We have this relationship for E phi, right? This one. And initially we derived one equation for stress that was this equation over here. So I have substituted that E phi factor into this equation. So that sigma is equal to E phi into 1 minus capital R over R, right? So if I substitute this one, I will get this equation. I have just replaced that E phi factor with this factor over here. This E phi has come.
Okay.
And this other equation for stress remains the same.
Right, sir.
So now we have three relationships. One is for the stresses, one is for the location of neutral axis, and the other one, this is also for the stresses, but it doesn't include the factor of movement. And in this factor, we also had to calculate this phi factor. So by replacing with the movement with this E5, we have got rid of two other factors that are capital E and capital Phi. So it has basically made up, it will make our calculations easier. So this is it from this class, and we will meet at 11 and continue this lecture.